All right, thank you. Thanks for the introduction, and thanks to the organizers for accommodating this session. And I think maybe it came a little late in our planning, but I'm happy to be here. And as Yasik was saying earlier this morning, I haven't been at the first XLDB, but maybe I was here at the second or third. And I've been at several of these. So I remember over time how these meetings went, and actually the last one I attended was also in this particular facility. And I remember in the old days this was a really exciting place to be because you would hear experiences from the field, from people actually doing big data stuff and talking about it at a time when we were all wondering, what is all this Hadoop and MapReduce and so on. And I think it's interesting to see the topics that are being discussed here in this meeting, because in a way it is, again, I think, showing where the action is. And I think now we are seeing that the action may not necessarily be in the core technologies, but sort of where the rubber hits the road, right? Where the actual interface between applications and, I would say, technology and applications is happening. And I think that's also sort of the context for what I would like to say here in my presentation. So this is going to be more about really trying to set a stage, maybe try and air some ideas and actually get your inputs, whether you want to ask questions at the end of the talk, or I'm certainly here for the full meeting, so in discussions later on. So what I'd like to do is set the context a little bit, and this will be from the NSF point of view. You had a lot of NIH stuff so far. Good, but I think there are a lot of things that NSF can do that can also help with a lot of these problems that you're seeing in the biomedical and medical domain. Talk about the opportunity as we see it, and then the questions. This is where we'd like to know how should we proceed. What are the challenges? What are folks seeing, and so on. And this is all in this context of what we are thinking of as sort of common infrastructure for sharing models, which in a way is the next challenge, right? I mean, all these years and decades we've talked about data sharing, metadata, how do we put common repositories up and make access to them and so on. But with all the huge amounts of data that are out there in any application domain or discipline you can think about, the next thing is really the models. I mean, the reason we collect all this data is because we want to learn something from them. We want to run machine learning or other kinds of models, and it's that learning that we now want to share and maybe compose those things together to create more complex systems. So what are the issues of trying to share at that next level? So in a way, you can think about model as sort of the first-class object, is what you're talking about here. The context for this is, and I'll say a little bit more about this, NSF last year went through a strategic planning exercise in terms of thinking about research directions for the next 5, 10, 15 years, came up with this notion of 6 big ideas that I'll mention, and also we'll talk about why that provides the context for these kinds of things. One of the things that came up in the NSF discussions was this notion of convergence, and convergence is really sort of multidisciplinary research taken to the next level. So it's really this sort of very deep integration of all the knowledge, techniques, and expertise coming from multiple areas, from technology on one side, from science or the application domain on the other side. And I think several of the talks you heard today had that flavor of it's not just providing a big scalable database. It's about understanding your data. It's understanding what kind of users are using it and what kind of interfaces there need to be. So it's sort of this deep integration, and also even at the technological level and algorithmic level, the kind of algorithms we design will depend a lot about, based on our getting true understanding of what the application is, what the needs are, and so on. And that goes to notions of data quality, how do you manage error, how do you manage provenance, and you don't get a good understanding of all of that unless you are really deeply understanding what the application is doing. So that's this notion of convergence, all of these coming together to form new expanded frameworks for addressing big problems, right, at the scientific level and the societal level. And of course, the other context is the ubiquity of data. So regardless of, take all of these 6 research ideas that I'm just going to mention shortly, regardless of what you're doing, whether it's in basic research, whether it's in applications, we just see enormous amounts of data everywhere. So this leads to the question of how do we manage all of these models that we are deriving from these data-intensive environments. So the big ideas for NSF, at the top you see these 6 big research ideas, one of which is really what we call harnessing the data revolution, or HDR, which is really about data science. So that's the big idea of related to the fact that we have all of this data coming at us, and we need to really take a new look at what kind of, it's not as if NSF or NIH or science in general has not seen data before. It's just that the rate at which it's coming at us, the complexity, and the rate at which we have to process it in order to provide maybe real-time or online, at least, results. So that's the harnessing data revolution big idea. There are a few others. There's another one that is really about the future of work. It's called Work at the Human Technology Frontier. So all of these technologies that we are bringing in, AI, machine learning, autonomous systems, et cetera, how are they changing the workplace of the future? And what does it mean for training and education of our current generation to prepare them for the next generation? There's another on navigating the new Arctic. There are enormous changes going on in the Arctic region. What does it mean for, I guess, the planet in general and the people who live around the planet, not just people who live in the Arctic? What kind of observing systems and modeling can we do to sort of do predictive things about what's going on there? The fourth one is on windows on the universe, which we also call the multi-messenger astronomy. At least one of those projects is something that Jacek used to be involved in before, which is the LSST. But there's LIGO, LSST. There are all these new ways by which we are able to observe what's going on out there in the universe, and deploying some of those things and processing all of the data that's coming at us. That's one of the other big ideas. Then there's the quantum leap. So this is sort of trying to address the post-Moore's law issue of, what's the next generation of technology going to look like for computing that can also deal with all these huge amounts of data coming at us. And finally, understanding the rules of life, which is really connecting all the genomic level information all the way to the phenomic to try and understand, sort of predict the phenotypes. So those are the 6 big ideas. There are some other so-called process ideas, one of which is convergence that I already mentioned. But the point of talking about all of those ideas is that they all involve this notion of convergence and bringing data together in very deep ways from different heterogeneous sources. There's one more context that's going on relevant to what we're talking about here, which is over the years there has been work at trying to represent models and share models, starting with the work in PMML, predictive model markup language, portable format for analytics, which is trying to help analytic processes run on different platforms more easily. More recently, work in systems biology markup language that NSF has funded. Now NIH is also picking up some of that, and so on and so forth. Guidelines for recording information about simulations. And we are beginning to see resources. So there's the biomodels database for sharing computational models in biomedicine. There's a recent announcement from Google on TensorFlow Hub for sharing machine learning models using TensorFlow. So that also sets the context that there are these kinds of things beginning to happen. And there are, and as I said earlier, there are all these research opportunities where there is a need. So the big ideas and the notion of accelerator that I'll just talk about shortly make us think a little bit about what are the kinds of environments we want to create to support those kinds of big challenges that are coming up. The other opportunity, of course, is that there is also new initiatives at NSF. So the second bullet there is talking about a budget commitment to support some of these things. And that's public information. What I've shown you there, you can get from the NSF website. It's the 2019 budget that the administration has sent to Congress. where each of those big ideas that I mentioned, the 6 big ideas, have $30 million per year of new money, money dedicated to those ideas. For 5 years, hopefully more, but at least for 5 years, $30 million. In addition, a couple of the big ideas, which is the Future of Work and Harnessing Data Revolution, HDR, have an additional $30 million for this idea of an accelerator, which I think is an important opportunity for this, especially this community sitting here in Silicon Valley, where there's a lot of interactions between universities and industry and so on. The notion of the accelerator, for those of you who might be familiar, the NSF accelerators will be a little bit more like a DARPA project. DARPA projects are very focused, have an objective, have a goal to achieve, typically have very short life cycle, turnaround cycles, I should say. I've been on DARPA projects, some of you probably have been, and every quarter you have to go to DARPA and report your progress, okay? So that's sort of going to be the flavor of these accelerators, and there's and the other aspect of that is that the $30 million invested there needs to find $20 million of matching funds in industry or from other agencies. Other agencies could be NIH, could be DARPA, NASA, et cetera, et cetera. So if you really add it up, it's potentially $80 million of new money every year. And so that's an opportunity for us to think about how do we really garner all these funds together to really make progress on this harnessing the data revolution idea. So I did it very quickly, but hopefully you got the message that some of the 6 big ideas that I talked about are really large-scale things, and that you can imagine all of them generating huge amounts of data, requiring a lot of this machine learning, deep learning, et cetera, all sorts of sort of data-intensive modeling along with simulation models. And you can imagine that in all of those cases, and remember when you talk about NSF big ideas, you really are talking about foundational and basic research. It's not even sort of applications of today. It's about doing research for discovery purpose. But even in those environments, you can think about not only sharing of the data, but sharing of the models that get generated by doing, whether it's windows on the universe or, well, even Quantum Leap, for example, we've been talking with our material science and other colleagues at NSF that there's a lot of data generated in just trying to understand what materials are good in the case of quantum computing. So there's a lot of data mining involved in just even designing those systems and the materials that go into them. And not only the big ideas, there are a number of cross-foundation efforts even at NSF ongoing that would benefit from these kind of model sharing ideas. So for example, Smart and Connected Communities, that's a program that is at NSF related to, a lot of it is related to optimizing infrastructure, whether it's transportation or the electric power grid, water systems, et cetera. And the point is, if we funded a research that did some kind of, say, traffic modeling in a particular urban area, say Dallas, Texas, could that be used in another urban area, say Miami, Florida? And if it can't be, why not? What's the difference? Why is this model that was generated in one place not being able, not working well in another place? And when you start thinking about this at the model level, you sort of get more insights about what's actually going on. So there even exists, and certainly Secure and Trustworthy Cyberspace, that's our cybersecurity program, SATC, also generating lots of data and doing model development in that context. And so any number of even existing programs are now moving to the place where it's not just about collecting data ab initio and doing some small analysis on that, but it's actually about sharing the models that you've generated from your research so that the next researcher can actually use that and build on top of it, okay? And of course, all of this will also help with reproducibility, which is a big, big issue. Now everybody is concerned about, the result that you produce, can I reproduce it, okay? So what are the questions given all of that? So if we are interested in creating some kind of a common infrastructure that enables us to share data-intensive models, What should be the research agenda for doing that? What should be the infrastructure to support that? Part of the reason you might want to share models is because if you have a machine learning model that has been developed in one context, it's much faster if you can adopt that model than rather than having to train a brand new model, because a lot of the time is in the training of it. So what permits models to be reused? Could you reuse could you do things like transfer learning? Can you reuse certain levels in a machine learning, deep learning model and then only train the others? So you start getting into sort of research issues of what does it mean to reuse these things. So we might want to look at what are the methodologies for how do we record these experiments? So how do I describe how did I collect the data set? How did I clean up the data set? How did I use it for training? And how much of all of that is useful or needed if I'm going to reuse that? What would be the standards for recording all of these things? What would be the tools? How could I query? You can even think of this as a database problem. If I had all of this model repositories out there, what kind of query languages would I want to have that allow me to understand what's in that model, what can I reuse, and how do I understand what's already existing? And then, of course, what resources do we need? Today you heard more or less, I don't know if all the talks, but you heard a lot about cloud-like environments. So clearly having something like that is good for sharing. And in the process of all of this, we are also interested in building up these notions, essentially building up the notion of trustworthiness of models. And how does a model become trustworthy? So you have to think about ideas of transparency, interpretability, reproducibility. Interpretability, by the way, is especially important because you might have developed model in one context for the work you've done, but if you want somebody else to reuse it, it should be easily understandable as to what was done without sort of having to go down to a code level or whatever. What are the challenges? So if we did come up with all of this, if we did come up with a cloud environment, came up with standards and came up with methodologies, so sort of think of this as kind of like doing software engineering, except you're doing it for data-intensive models. Well, how do we actually make sure that people follow the software engineering principles? In other words, how do you make sure, so what are the incentives, what are the mechanisms we could have in place to make sure that people actually follow these methods so that models can be reused? Right? Part of it is, so there are incentives, but part of it is also having the right set of tools. If it's easy enough to do, people will do it, right? And then what are the incentives for doing it right, what I call doing it right the second time? In other words, what is an incentive for me as a researcher to say, I'm not going to write a proposal about doing something brand new. Let me see if I can build on top of what somebody already has. Some of that comes from the funding side, because you want to have programs that actually say, we're not going to let you create new data. This is a program that's about reusing existing data, right? But also, the only way, again, that happens is if it's going to be easy enough to do that. So that's my pitch. It's a very quick pitch to say that we see, by the way, I mean, we've been thinking about this for more than a year, maybe 1.5 years or so. And some of the original ideas came to us by actually talking to some of the big data companies, the typical ones you might think about, who were already telling us at NSF that they are building internal infrastructures for sharing these kind of models, because if a lot of work has been done in training models, why don't you just try and reuse it rather than spending all that effort again to retrain in a new situation. So it's something that we are very interested in exploring. There is a couple. I also, by the way, should thank Arun Kumar, who's here, is one of the organizers who I think gave me the idea that maybe I could come here and pitch this. And so in return, I'll pitch his workshop. So Arun and a bunch of folks are running this second workshop on data management for end-to-end machine learning, the DEAM workshop at SIGMOD. And then we have a workshop that was accepted at KDD on what we're calling common model infrastructure. And the organizers include folks like Amol Deshpande from Maryland and Bob Grossman, whose name I saw in the biosphere slides earlier. So Bob is in Chicago, Bill Howe from Washington, Luke Wan, who used to be at NSF with us, and now he works for Baidu, and Arun himself, and Vandana Janeja was one of our AAA's fellows at NSF. So that's all I had, that's all the pitch I wanted to make, and I'm actually open for any questions or comments. I'm not sure how I'm doing on time.
We are a little bit behind, but maybe we can take one question.
So very quickly, models is a word that gets thrown around a lot. Models tend to be incredibly idiosyncratic, right? A hierarchical clustering model is different from a regression model, is different from a deep learning model, and so on and so forth. I'm just wondering, just to sort of, if you wouldn't mind taking 2 minutes to step down one level, what do you mean by model, and what common themes are there between, for example, a hierarchical clustering versus a machine learning or a deep learning model?
Right. Well, actually, by the way, this is one of the things we'd like to explore. That is, how much of these can be reused? So the examples I gave you earlier of some of these model description markup languages, etc., are really a lot more about computational models. And these are models that appear in papers where somebody might have done certain kinds of simulation or reaction processes and built up a model of how a cell works, let's say. And that's a model in that case. But I think we are also interested really in machine learning models where so the very first set could be things like supervised learning, where you have large data sets that you have worked on, created a machine learning model, and then the question will be, can I reuse what you did? And the example I gave you, like say traffic in a particular city, right? So if I have a model for predicting traffic jams in a place, could I reuse that? And we've actually had conversations with some of the some community folks who have developed machine learning models for predicting flooding, for example. And they've realized that they've developed it in Texas, and a model developed for flooding in Texas would not work, let's say, in Connecticut. And it has to do with hydrological and geological dependencies because how the soil works, etc. But like the person himself was saying, but it may work in a neighborhood a little bit away from where they developed it, which gives you and that's what I mean by model as a first-class system, because that starts making you think about, well, so why is that? How far can I take this model? In this particular case, it's a geoscience or geology dependency that came out. But if you think about something like traffic, why does it work and not work? I think it gets you to start thinking about a next level of sort of insight into what's going on. So yes, it could be a broad range, and we'd like to know where this kind of sharing can happen and where it doesn't, may not happen as much.